Okay. No, this. Oh, okay. Is that either not going to work or it's going to work its way in?
Is that pyrrole?
Yeah. There are a number of molecules out there that are aromatic and are not hydrocarbons. They contain other atoms, and there is a important class of biological molecules called alkaloids that contain nitrogen, and many of the alkaloids are themselves aromatic. Let's look at some of the very, very simple molecules, because we're going to see two of them, and they're going to be the framework for recognizing what's going on in much more complicated molecules. This molecule is pyrrole. Does pyrrole strike you as being aromatic? No, on the surface it's not, because we've trained our brains to look for 3 pi bonds in a fully conjugated system, okay? Because pi bonds are movable. And if we can move them, and we can put them 1 bond away from each other so that they're conjugated, then we can delocalize their electrons. But what else is also movable other than pi electrons? And does nitrogen have a lone pair of electrons?
Yes.
Yeah. So a lone pair of electrons, a single bond away from a pi bond, is now also movable. So I can build my big molecular orbital, instead of needing 6 carbons in a hexagon and 3 double bonds, I can do it in a pentagon with 2 double bonds and a lone pair. Okay, so nitrogen should have 3 bonds and a lone pair. It's group 5. 1, 2, 3, 4, 5. That gives it a bonding electron, a bonding electron, and a non-bonding pair of electrons. So if we see 3 bonds to nitrogen, we don't expect a charge. We do expect a lone pair of electrons. That lone pair of electrons could stay as a localized pair on that nitrogen and be used as a base. Or it could serve a higher purpose and donate itself into the ring, and then be delocalized and make this ring aromatic. It has 4m plus 2 equals 6. Not exclusively calling them pi electrons now. I have 6 mobile electrons. This is aromatic. And it's fully conjugated because it goes two movable electrons, single bond. 2 movable electrons, single bond. 2 movable electrons, single bond. This molecule is planar and cyclic, fully conjugated, and therefore is aromatic. Okay. Let's draw all the contributing resonance forms. So I was telling people in my office hour this morning, the question that everybody attempted with differing degrees of incorrectness on the test was the resonance hybrid question. So you're getting that as a homework that will be due on Friday. There is no lecture class Friday. I'm in Denver. So I will give you homework. It needs to be waiting for me under the door when I arrive on Monday, which means do it on Friday. Okay. Here's how we draw the contributing resonance structures for pyrrole. You write the framework. And you come to the realization that that nitrogen has a lone pair of electrons. It's not in the ring yet, but you're going to put it into the ring, because if you put that lone pair of electrons into the ring becomes aromatic, which is a dramatic lowering in energy. It's a big stabilization. If you don't put the lone pair of electrons into the ring and leave it to be a base, then the molecule doesn't get to be aromatic. Okay. So the electrons are going to go in to the ring from the lone pair to the middle of a bond. I'm building a new carbon-carbon double bond. I'm building a pi component right here. That carbon already has 4 bonds, because there's a hydrogen here we can't see. And then 2 bonds to that carbon and 1 bond to this nitrogen. If that carbon already has 4 bonds and you're trying to build a new bond to it, something has to give. The weakest bond will break. And what is the weakest bond? The pi component of the double bond. Am I activating or deactivating this ring? I'm activating this ring. Like, is this electron donation or electron withdrawal? Putting the electrons into the ring. I'm donating those electrons in. Okay? Double-headed arrow. Only the electrons associated with charges, lone pairs, and pi bonds can move. I've built a new double bond right here. And this arrow, I've taken electrons that were in a pi bond and localized them on this carbon. So the arrow ends at an atom. What happens to that atom in my next sketch?
Charge.
What kind of charge?
Negative.
Electrons are negative. If the arrow dead ends on an atom, that atom now goes negative. Okay. Well, if I've got a negative in my sketch, that means I have to have a positive in my sketch somewhere else to even things out. Where does the positive go? That nitrogen has 4 bonds. A nitrogen with 3 bonds has no charge. A nitrogen with 4 has a positive, and a nitrogen with 2 has a negative. All right, we see this before, so. 0 charge. If I go up, we'll do it with the ammonia ammonium amide. 2 bonds, 3 bonds, 4 bonds. It's just the same as water. 2 bonds on oxygen, no charge. H3O plus. 3 bonds on an oxygen, positive charge. Oxygen, negative charge. Okay. Look where you are on the periodic table. Nitrogen is in group 5. 5 plus 3 is 8, so therefore nitrogen makes 3 bonds. If I increase the number of bonds, I go positive. If I decrease the number of bonds, I go negative. That nitrogen needs to be a positive. Okay, next sketch, what do you do? Move the negative charge. Do I move it towards this positive? You telling me I can't do this?
You already did that.
I already have. It's that arrow right there. Take the charge, which is really a lone pair of electrons, and push it towards the pi bond. Going to make a new double bond here across the top. That carbon already has 4 bonds, so it has to let go of a bond, and it lets go of the pi bond, and then dead ends it onto that carbon. So this carbon now gets the negative charge. Okay, what you do next?
Move the negative towards the positive.
Like this?
No, towards. Onto the negative.
Does that make the positive go away? No, it doesn't. If we had 6 atoms in this ring, it would make it go away. But we have 5, and 5 is an odd number. And every time we scoop these electrons around, we move things an even number of positions. We're going to go around the ring twice. We're going to go around the ring twice. It's not that bad, because it's a very small ring. I'm going to make a new pi bond between this carbon and that nitrogen. That nitrogen is already holding 4 bonds. So when I make a new bond to it, it has to let go of something. It's going to let go of its weakest bond, and its weakest bond is positive on the nitrogen go away? It still has 4 bonds. That nitrogen still has 4. Keep the positive on it. Next.
Negative move towards the
Move the negative towards the pi bond, and we end up doing this. then finally, take that negative, push it towards the pi bond. That pi bond now breaks and puts the electrons back on the nitrogen as a lone pair of electrons. So we've gone completely around the ring. Because the ring was a 5, we had to go around twice. We have 1, 2, 3, 4, 5, 6. It might look like a lot more than a benzene ring, but all the benzene derivatives had 5 contributing resonance structures. This has 6. Okay, draw the resonance hybrid. The resonance hybrid is the thing that takes into account, was there a double bond here? Was there a single bond here? Was it there all the time? Was it there part of the time? Was there a charge on this atom? Was it there all of the time? Was it there part of the time? Congregate all of these together to make the resonance hybrid. None of the sigma bonds have moved, so the framework is here. Now all I'm going to do is pick an atom, work yourself around the ring, and figure out, was there a single bond or a double bond here? Was there a positive charge or a negative charge here at any point? And what's the overall effect of moving those electrons around look like? Where do you want to start? Let's start at the hydrogen, right? The hydrogen is singly bonded all the time. The nitrogen, some of the time it's neutral, meaning uncharged, and then most of the time it has a positive charge. So I'm going to put somewhat of a positive charge on that nitrogen, delta positive. Let's look at the bond between the nitrogen and the carbon to its immediate right. It's a single bond, it's a double bond, single bond, single bond, single bond. So some of the time, that's a double bond, but not all of the time. This carbon, no charge, no charge, no charge, negative, no charge, no charge. So it has a negative charge on it some of the time. This carbon-to-carbon bond is a double bond, is a single bond, is a single bond, is a single bond, is a double bond, is a double bond. So that's a double bond some of the time. This carbon has no charge, has a negative, has no charge, has no charge, has no charge, has no charge. Some of the time it's a negative. And you work your way around and you find that inside that ring, every bond has something of a multiple bond character. And all of the carbons carry a small negative charge. This molecule is aromatic. What do we do with aromatic reactions? What's our reaction for aromatic systems? So we'd be looking to do electrophilic aromatic substitution with something that's positive. Is it going to react with this ring? Yeah. Where is it going to react with the ring? Everywhere. This, so what's carbon number 1? Trick question. There is no carbon number 1. That's the most important place in this molecule because it's the most interesting. So that gets to be number 1. But it's not a carbon. That's now called N1. Position number 2 is here, and we now call it C2 to tell the reader that there's a bit more going on than you might think. So we have an N1, C2, C3, C4, C5. An electrophilic aromatic substitution apparently is going to occur everywhere. Apparently. It might. It might not. How many unique sites for electrophilic aromatic substitution are there in pyrrole? Just the 2. Because this molecule is symmetrical right down the middle. Which means these 2 are the same as each other. Those 2 are the same as each other, but different than these 2. Okay, let's do it. Okay, audience participation time? Yeah, I think so. I think so. Let's do two competing reactions on the board. And see if there's a difference. Volunteer. Because before there are people who are told what to do, there are volunteers. And you're just making yourself known to me now. We'll help. You get the blue pen. It's the nicest pen. Yeah, but it's nicer than the other pen. I will help. I'll show you. And while that's going on, over here in the black, we're going to have electrophilic aromatic substitution. The carbon number 3. Who looks the most scared? Okay, so, yeah, no.
I want to be on the video.
What's our electrophile? Let's do something useful.
One of those.
Okay. Yeah? Okay. Draw an arrow, draw what you make. But we're going to put your substituent here. Okay? Yours is going to go there. Same double bond is going to be involved in both mechanisms. It's an electrophilic aromatic substitution. In the first step, the pi bond reaches out, grabs hold of the electrophile.
Is here?
Yeah. You need.
Wait, this.
No,
You said to put it there.
that's not attached to the nitrogen. It's going to go here. And you need. So if this pi bond breaks and this carbon gets the substituent, what does this carbon get? Yep. We need a hydrogen right here.
Oh, this is where it dumps into here.
Okay, and then finish up. So the electrophilic aromatic substitution is that easy mechanism, and it's the same thing every time. You broke this pi bond, substituent on one of them, positive on the other. Okay? All right, just fine. Thank you. Now, something is going to stand out to tell us that although the resonance hybrid told us all 4 of those carbons were activated towards electrophilic aromatic substitution, these 2 positions are not equal. Oh, and by the way, if we were grading, I need a red pen. If we were grading what's on the board out of 10, are they 10s? I know.
Like little numbers.
I'm not even looking at
We got
the
hydrogen proton.
substitution. Substitution has to have something leave. Okay, so in electrophilic aromatic substitution, pi bond from the aromatic ring opens out, grabs hold of something. Here we did it at carbon 2. Puts a carbocation on the other carbon. The hydrogen dumps its electrons back into the ring, re-establishes the aromaticity. Now I have a substituted aromatic molecule. Same thing, same thing, same thing. Carbon 2, carbon 3. Here's the big question. Which one wins? And why? And it's staring you right in the face. Okay, let's start with carbon 2 versus carbon 3. Which one wins? The answer is not here. And the answer is not here. And the answer is not here. And the answer is not here. The answer is in the intermediate. Which one wins?
C2.
I have one answer for C2. Anybody think C3 wins? Anybody else thinks that C2 wins? So far you're on your own.
I'm gonna go with C3. Just to
I have 2 for C3, and I have 1 for C2.
Where's C2 back here?
Both of you? It's 3 to 2.
Shane.
Yeah.
I don't know. I don't know if I'm doing. Shane's voting for C2. So you said.
Excellent.
Coming off the, what did Michael choose?
This is probably right.
I'm going with
Why? You did this one. You have no trust in your own work?
because I feel like if it's further away, maybe it's more stable. I don't know.
What's further away from what?
What we just added is further away from the NH2, so I figured maybe it was more stable. But
Okay.
not all in one position, but I
Okay.
don't really know that.
Okay.
I just know this is different resonance.
All we've talked about is resonance. Why would the answer be anything other than resonance? The answer is resonance. That's all we've been talking about. The answer is this carbocation versus that carbocation. Which one's better? That one or this one? I need somebody to change their mind. The whole thing about science, why science will succeed and humanity will prosper, is that science lets you change your mind. This one is allylic.
I picked C2.
I did pick C2.
What kind of carbocation is this?
You want special. Primary.
On its own. It has no resonance, and resonance always stabilizes the molecule. E.A.S. occurs at carbon number 2 or 5 first. You will do reaction at carbon number 2, and then you will, and I don't care whether it's an activator or a deactivator, and then you will do E.A.S. at carbon number 5, and I don't care whether it's an activator or a deactivator, and then, and only then, will you do E.A.S. at carbons 3 and 4. Okay? Let's do some. So electrophilic aromatic substitution for pyrrole occurs at carbons 2 and 5 first, and then 3 and 4.
But we don't have to counterclockwise, right?
That raises an important question. Why is this carbon 2 and carbon 3, and that's carbon 4 and carbon 5? Why are we numbering counterclockwise? Why do we do that? The answer's really dumb. It doesn't matter, but we do it. Why do we do it?
Because some stupid person said to do it that way.
No. No. No, no, no. What goes here?
Yeah.
What goes there?
What the fuck?
The other reactant goes there. We've used the lowest numbers next to the reactant. That's why. There's absolutely no reason why this is not carbon number 2, other than I'm going to substitute to this ring in a second. And I'm going to put that substituent at the lowest numbered position. The only reason that we number our rings counterclockwise is because it works better. I get the lowest numbered position. That's all. Okay, let's do some chlorine right here. What do I get? Oh, by the way, have you seen my pyrrole? Am I standing in the way? Have you seen my pyrrole? It's not a pyrrole anymore. This is now a furan. Is furan aromatic? Yeah. Oxygen has 2 lone pairs of electrons. Does it put them both in the ring? That would be really dumb. Why would putting both sets of non-bonding electrons into the ring be really dumb? I'd break Huckel's rule, and I'd make an anti-aromatic molecule if I put 8 electrons into the ring. So oxygen uses 1 set of its lone pairs to be in the ring, and the other one doesn't make it into the ring. Okay? where does the nitro go? Here, here, or here. Only when both C2 and C5 have been occupied will you move to C3 or C4, and I have no way of predicting which one gets it. You'll get some of this, and you'll get some of that. Both of them are available, C3 and C4, and I can't really tell which one's going to be which. Okay? So pyrrole and furan belong to a series. This is pyrrole. And this is furan. And this is thiophene. And they all do electrophilic aromatic substitution at all 4 carbons in that ring. Pyrrole is better than furan, and furan is better than thiophene. Can we figure out why? So they all do it, but the ability of pyrrole to do electrophilic aromatic substitution is a bit better than furan's, and furan's is better than thiophene's.
Basicity. Is it basicity?
Close. So what trends do we have? Well, we've got a trend from, so we can't do all 3. What's the trend between nitrogen and oxygen? Hmm?
Their electronegativity?
What's the difference in their electronegativity?
Nitrogen's more electropositive. Or oxygen's not.
Oxygen is more electronegative. And what does electronegativity mean?
Tendency to pull electrons towards itself.
Pulling electrons towards yourself. What does the aromaticity of this ring depend on?
The domination of electrons.
Putting the electrons into the ring. So if you're pulling, if you're holding them back, then those electrons don't go into the ring quite as much. So this one is a little less aromatic than this one, because the electronegativity here is a bit stronger. Okay. What about the difference between oxygen and sulfur? What's the obvious difference between sulfur and oxygen on the periodic table? Size. Sulfur is significantly larger. And if we're thinking of orbital overlap between, here's an oxygen and here's a carbon, the p orbitals that make that sigma bond are the same, they belong in the same family, they're in the same period. Carbon and oxygen are in the same period, and carbon and nitrogen are in the same period, But now I've got, here's a carbon, and its p orbitals are this big, and here's a sulfur, and its p orbitals are this big. And the overlap's not as good. So these three belong to a series, and they are all interchangeable. If I ask you to know what's going on with pyrrole, I expect you to know what's going on with furan, and I expect you to know what's going on with thiophene, because they're all the same. They're just one slightly better than the other. Okay? These are the activated molecules. We'll keep, because I don't need you to learn two sets of reagents, but pyrrole is so activated towards electrophilic aromatic substitution that, you know, this Lewis acid, don't really need it. I can switch that out for a weaker Lewis acid. And the textbooks will write BF3 under here. That's a weaker Lewis acid catalyst. Why go ahead and memorize a whole new set of reagents for a special case? The Friedel-Crafts reactions work significantly faster here. And there's no worry about, oh, but I've got a deactivated ring. These reactions are not available to me because I put a nitro on this ring. No, doesn't matter. Pyrrole is so activated that it overcomes whatever deactivation you put on the ring. It doesn't matter. Let's look at one more. There's another molecule. And this one's a fantastic molecule. I love this molecule. I used to threaten that one day we will have a smell lab where you just come to lab and we go to the stockroom and smell stuff. Because everybody should know what this molecule smells like. This is pyridine, and pyridine, some people think it smells awful. It kind of does. But it has just a little, you know how bulldogs are so ugly they're cute again? This smells so bad that it's almost nice. It's like fish and metal and rotting fruit. Yeah. And if you smell it, you will never be able to forget what it smells like. You just, smells one of those things that you can recall. You think how I can practically smell it now. And it's a good thing you can smell it because it makes you sterile. Exposure to this makes humans sterile. I think you have to be prolonged exposure to it. So it's good to know. You can't miss it. I mean, it's not leaking from, I don't know that we even have any in the stockroom, but none of it will leaking from the stockroom because everybody would know in a second. All right. That is a 6-membered ring with 3 pi bonds. How many bonds to that nitrogen? 3. What's missing from my sketch? The lone pair of electrons. Is the lone pair of electrons in the ring or outside the ring? Why? That ring is already aromatic with 3 pi bonds. If I put the electrons from that lone pair of electrons into the ring, I would make the ring be anti-aromatic, which would be a big boneheaded move. So pyridine has an active lone pair of electrons. Having a lone pair of electrons opens up a world of chemistry to you as a role of a base. This is a base. Was pyrrole a base? Pyrrole has a nitrogen and a lone pair of electrons. But that lone pair of electrons was used to build the aromaticity. So pyrrole is not basic. Read questions on the previous year's tests. Tell me the difference in basicity between, explain the difference in basicity between pyrrole and pyridine. Pyrrole needs the lone pair on the nitrogen to go to the aromaticity. It's using the lone pair for something higher than being a base. Pyridine absolutely rejects the lone pair of electrons from coming into the ring. That's now a hot lone pair. This is a good base. Pyridine is a liquid. Turns out to be a very good solvent. I've done a number of reactions in pyridine over my time. You do have to get the stink out of your product at the end. But there are a couple of reactions that we do that use pyridine as a solvent. All right, let's do the resonance structures. I have 3 pi bonds and a lone pair of electrons and an electronegative atom. Where does my first arrow go? Let's figure this out. How about I do this? I take that lone pair of electrons and I push them towards the pi bond. How does that look? If I do that, the ring goes from having 6 pi electrons to having 8 pi electrons, which goes from being aromatic to anti-aromatic. This is a solution only on paper that would never ever exist in real life. That is a huge uphill climb in energy. No, molecule rejects that move soundly, says no thank you. This way, from the pi bond to the electronegative atom. The nitrogen is more capable of holding on to electrons than anything else in this ring. Take the electrons, put them on the nitrogen. We have run out of time, but what have you just done? Have you activated this ring or deactivated it? Can we all see that this is now a deactivated ring because we've pulled electrons out of the ring? That's the first step. See if you can finish the remainder. What goes to the nitrogen? The electrons end at the nitrogen. So the nitrogen in your next step is negative, which means this carbon is. See if you can finish it. We'll pick it up on Wednesday.